Hello everyone. So far we have discussed that if I keep a positive charge in an electric field, it experiences a force Q into E, if E is the intensity of the electric field and Q is the charge in the direction of the field. If I put a minus charge in an electric field, it experiences equal force but in opposite direction, minus QE. Just imagine what will happen if I keep an atom in an electric field. Atom, and there is an electric field in this direction. Atom has equal number of protons and electrons. Each proton will experience force, each electron will experience force, but it will be in opposite direction. So I can say that the net force is 0. So net force onto it will be 0 because positive will be pulled in the direction of the electric field and minus opposite to it. But okay, net force may be 0. But does it also mean that the atom behaves in an electric field in the same way as it behaves when there is no field? Then the answer won't be same. Why? See, when we keep an atom in the electric field, I just told you that positive charge, protons experience force in the direction of the electric field and minus opposite to it. So actually the centers of positive and negative charges in an atom, these centers are shifted. Center of positive charge, center of negative charge no longer coincides. Now it gets shifted to positive towards the field and negative opposite to it. So it means this arrangement where the positive and the negative charges are equal in magnitude but separated by some distance, we call electric dipole. So electric dipole is an arrangement where we have plus charge, minus charge separated by a very small distance. So I can say atom starts behaving like an electric dipole when we keep it in the electric field. If the field is very large, just think what will happen. If the electric field is very large, electrons are experience force opposite to the field. If we keep on increasing this electric field, this force on electron will keep on increasing, and it may also happen that at some point of time the atoms are stripped of these electrons. The electrons can come out of the atom also. That may also happen, but that will require a very large value of electric field. So anyway, now positive experiencing force in the direction of the field, minus opposite to the field. Atom placed in an electric field does not experience any net force, but it behaves like an electric dipole. Just think of some other examples of electric dipole. These are very common in nature. That's why the study of electric dipoles is very important and necessary too. Think of some molecules where the positive and negative charges, centers are not same. HCl, NaCl, even H2O, water. This angle is obtuse, it's around 104 degree. So in these cases, the positive and negative charges, they are not centered at one point. So these are all called polar molecules. We have two poles, one plus and one minus, or we can call that all these molecules are actually electric dipoles. So electric dipoles are very common in nature. All these polar molecules, they have some dipole moment. We will study how electric dipoles respond to the electric field. If they are kept in some external electric field, how will they respond? How will they behave? And further, we will also find out how much electric field is produced by an electric dipole. So in this class I will take the electric field due to electric dipole. So electric dipole is an arrangement of plus and minus charge, equal in magnitude, separated by a small distance, and we define a quantity. We call it electric dipole moment. Electric dipole moment. This tells us when we will study how a dipole behaves in an electric field, then this quantity electric dipole moment, this will be very important. We'll see how it responds to the external magnetic field, that to a large extent will depend on this quantity Q into L, the distance between the two charges and the magnitude of any one charge, because they are same. So coulomb meter, that will be the unit, SI unit, and it is taken as a vector quantity and its direction is always negative to positive charge. So for this dipole, this is the direction of dipole moment. So dipole moment acts from minus to plus and is equal to the product of either charge and the distance between the two charges. This is the electric dipole moment. We will be using it while deriving the expressions for the electric field. So we will take two specific positions for the electric dipole and then calculate the electric field at those two positions. So first one will be electric field along the axis of the dipole. So I have a minus charge and I have a plus charge, L the distance between them, and let me take a point P at distance R from the center of the electric dipole. I need to calculate the electric field at P, and it's very simple. We have already done what is the electric field due to a point charge. Electric field due to a point charge is 1 by 4 pi epsilon naught Q by R square. So we shall be using this expression here. We will find out the field at this point due to plus Q charge, the field at this point due to minus Q charge, and we'll find the resultant. So what is the electric field at P due to plus charge? This plus 1 upon 4 pi epsilon naught Q upon square of this distance. This is R, this will be L by 2. I have taken it from the center, so this is L by 2. So R minus L by 2 square. And its direction, how do we find the direction of electric field? We assume that there is a positive charge at that point, and then we see the direction of force on that charge. So if I take a positive charge here, due to this will be repelled. So this is the direction of plus charge. Electric field due to plus charge. Now electric field due to negative. This 1 by 4 pi epsilon naught Q upon this distance will be now taken. So R plus, and what will be the direction? Due to minus, if I assume a positive charge here, it will be attracted. So the direction of the field will be this. Electric field at P due to plus charge away from the dipole, and because of minus it is towards it. Now in order to calculate Newton per Coulomb SI units, what will be the resultant field? It will be the difference of the two, because two vectors in opposite direction. How do we calculate the resultant? Take the difference. And which one is bigger? Denominator has a less number, a smaller number, sorry. And here the denominator is a bigger number. So this will be smaller, this will be larger. So it will be E plus minus E minus. Had there been minus on this side and plus on this side, then the field due to minus would have been larger. So take the difference now. I can take 1 upon 4 pi epsilon naught q as common, and it becomes r minus L by 2 square minus r plus L by 2 square. We'll have to solve it, and this will be the final answer. Let me write this expression here, 1 upon 4 pi epsilon naught q. It's simple algebra. A minus b, a plus b. It becomes a square minus b square. So r square minus L square by 4 square. A minus b and 2a minus b and square. So a square minus b square whole square. And here it will be r plus L by 2 minus r minus L by 2. If I solve it, r square plus L square by 4 plus RL minus r square minus L square by 4 and plus RL. The square terms will cancel out. We will have 2RL upon r square minus L square by 4. So this is the general expression for the electric field. I will use now one approximation which is always valid actually. Whenever I am calculating the field due to an electric dipole. In electric dipole we have seen it is the, suppose HCl or NaCl. The distance between NaCl is always very small in comparison to the distance wherever we want the field. So even if we want to calculate the field produced by one atom at the site of other atom, this will be much more than the distance between Na and Cl itself. And same way, the distance by which the centers of positive and negative charge get separated in the electric field, this is also very small. So in this term, R is always much larger than L. This R is much larger. So what this will reduce to? I can write it 2RL upon r raised to the power 4. So I have neglected this. I have taken this as 0. R square raised to the power. So it is now 1R gets cancelled. Q into L is P. So 1 upon 4 pi epsilon naught 2P by RQ. This is the electric field. So electric field due to a dipole decreases as R cube, not as a square, as in case of single charge. P, but dimensionally still you can see, because P has one length in it. So it still is depending on 1 upon meter square as far as dimensions and units are concerned. So 2P upon RP. Now what if I write this in vector form? Direction of electric field. What is the direction of the electric field? E plus is bigger. So net field is in this direction. And what is the direction of dipole moment? Minus 2 plus. So these are in same direction. So this is how we can write the field produced due to the dipole on the axial position, or we also call it end-on position. End-on position or the axial position. This is the field produced. Next, I will take the field on the perpendicular bisector. This time I have chosen this point P on the perpendicular bisector. Perpendicular bisector means a plane passing through the center and perpendicular to this axis. So I am calculating the electric field at this point at distance r. So it will be at same distance from both plus and minus. L is the distance. Now again, as we have done in the last expression, we'll find out the electric field at P due to plus charge, then electric field at P due to minus charge, and we'll take the resultant. So what is the electric field due to plus charge? It is 1 upon 4 pi epsilon naught Q upon r square. Now square of this distance. This is r, this is L by 2. So how much it is? R square L by 2 square plus r square, Pythagoras theorem, and then it is a square, so root and then a square of it. And what's the direction? Direction of electric field is always determined by the force on positive charge placed at a point. So if I put a positive charge, it will be repelled along this line. So this is the direction of E plus. What will be E minus? 1 by 4 pi epsilon naught Q upon r square. Again, same distance, this one, but direction is different. What is the direction? If I put a positive charge, it will be attracted towards it. So the direction of is this. E plus in that direction, E minus in this direction. How to find out the resultant of these two vectors? We will need an angle between them. It will come in terms of that. So one way is under root a square plus b square plus 2ab cos theta. We can use that expression. So it will be under root e plus square plus e minus square plus 2 into e plus into e minus into cos theta, the angle between them. So we'll need an angle. Let us assume this angle. And in this triangle, if I take this theta, this will also be theta. Theta can be written in terms of r and L, so no problem, we can assume it. If this is theta, this is also theta, and this is also theta. It's simple geometry. This is theta, this line is parallel to it, theta and theta. Okay. I will resolve both of them and then find out the resultant. Resolving E plus. This component is E plus cos theta, and this is E plus sin theta. See, whenever you have one vector and it is to be resolved, if this is theta, this is A, it becomes A cos theta and this is A sin theta. Because if we complete the triangle, this becomes the base. Base upon hypotenuse is equal to cos theta. And same way perpendicular upon hypotenuse, this is sin theta. So it becomes sin and it becomes cos. So this is how it is resolved. In same way I can resolve minus 12, minus electric field due to minus charge. It is theta from this side. Actually the component at an angle theta, that becomes a cos component and the other one becomes sin component. So this will be E minus cos theta and here we will have E minus sin theta. So see now, E plus sin theta, E minus sin theta. They are equal and opposite. You see, in terms of magnitude, both of them are same. So it means E plus sin theta, E minus sin theta, they are equal in magnitude, opposite in direction, so we cancel out. So these components cancel out. So what is the net field? The resultant field is the sum of cos components. So E plus cos theta and E minus cos theta. And they are equal, E plus and E minus. So I can write 2 into E plus cos theta or E minus cos theta. Q upon R square plus L square by 4 into cos theta. Now substitute the value of cos theta from this triangle. Base upon hypotenuse. This is L by 2 under root L square by 4 plus R square. So what is it now? 1 by 4 pi epsilon naught QL upon 3 by 2. This and this same, 1 plus half, it becomes 3 by 2. So this is the resultant field due to a dipole on perpendicular bisector. Now, again I will use the approximation that R is much bigger than L. So how can we write this expression? 1 by 4 pi epsilon naught QL, and I can simply drop this because this is almost 0. So R square raised to the power 3 by 2. So it becomes R cube. So R cube. What is QL? P. So 1 by 4 pi epsilon naught P by R cube. So this is the electric field. Now if I write it in the vector form, this is actually on this side. So if I write it in vector form, this will be actually minus E cos theta minus E plus cos theta. And P will be on this side. So writing it in vector form, this will be 1 by 4 pi epsilon naught minus P upon R cube. Now see the difference between this field, which is on perpendicular bisector, and the earlier which was on axis. 1 by 4 pi epsilon naught 2P by R cube. This field is double of it and in direction opposite. So if I take 2 points at the same distance, one along the axis, another one on the perpendicular bisector, then the field along the axis is double the field on the perpendicular bisector but opposite in direction. So along the axis, field is in the same direction as of dipole moment, while on perpendicular bisector, field is opposite to electric dipole moment for the dipole.